Recent deep image generation models, such as StyleGAN 2, has achieved high-quality 2D face image synthesis. However, they are confronted with the challenge of synthesizing 2D face images with multi-view consistency. We address this issue by proposing an approach for generating detailed 3D faces using a pre-trained StyleGAN 2 model. By leveraging StyleGAN 2 as 3D generator, we achieved the following goals. The first one is view-consistent face image generation. In our work, we train our 3D generator to synthesize 3D face meshes, and encourage their appearance to be consistent in different view. By rendering the generated mesh as images in different view, we can synthesize face images with their appearance consistent in different view. The second goal is compatibility, which means the appearance of our 3D face mesh synthesized from the latent code match the face image generated from the same latent code in StyleGAN 2. By continue training our 3D generator from pre-trained StyleGAN 2 and design the reconstruction loss for training, we inherited the latent space from the pre-trained StyleGAN 2 and further encourage the generator to output the appearance that match the pre-trained StyleGAN 2. The third one is explicit face attribute control. In our work, we use parameterized face model called 3DMM as our base blend shape. Instead of editing stylecode to control the face attribute implicitly, one of the advantage of using parameterized face model is that we can explicitly tune the attribute of face, and the change is disentangled to other attributes. Furthermore, compared to other plain image generator work, our 3D generator synthesizes face mesh, which provide more applications for downstream tasks. As we claimed above, our work is a generative approach to synthesize 3D applicable face meshes from the pre-trained StyleGAN 2. Given a style code, we can synthesize its corresponding 3D shape and appearance. With these information, we can render them as images as shown below. Our framework contains two main components. The first component is the 3D coefficients predictor. This component aims to predict the corresponding 3DMM coefficients given stylecode. Part of the 3DMM coefficients describe the 3D shape of the face, which provide the geometry information for rendering the face. The second component is the 3D generator. This component's goal is to generate the corresponding diffuse map and general displacement map from stylecode, which alternatively provide the appearance information for rendering the face. Leveraging modified StyleGAN 2 generator as our 3D generator, we synthesize the appearance from 3D generator to render face images for training. On the other hand, we utilize the StyleGAN 2 generator to synthesize the target images. These images are further be used in loss calculation for training our work. To encourage the synthesized face to have high fidelity quality and identity similar to the StyleGAN 2 one, we use reconstruction loss containing photo loss and perceptual loss to train our generator. The photo loss simply use L2 norm to measure distance between images, while the perceptual loss further extract the feature maps of both images, and then measure the L2 distance between the feature maps of both images. To calculate reconstruction loss only in the visible region of face, we render 3DMM blend shape with non-zero texture, and propagate valid gradients backward to extract the visible region on our face. By element-wisely multiplying the difference of both rendered image and target image by the mask, we excluded the reconstruction loss calculation in the unrelated region of image. However, we observed that in some cases, the synthesized texture failed in the other side of the face. To suppress this artifact shown below, we added multi-view loss to ensure the face appearance to be consistent in different views. The multi-view loss encourages the faces in both original and symmetric view to be consistent. So we additionally prepare symmetric view StyleGAN 2 image and its corresponding 3DMM coefficients for training. To obtain the symmetric view StyleGAN2 image, we propose a method called view angle shifting to turn the view angle of the original stylecode to its symmetric view. To shift view angle of stylecode, we first adopt the method described in interface GAN to extract the direction d in latent space to turn the yaw angle of the face. They propose to label desired attribute of stylecodes as two groups with extreme extent, and train a support vector machine, SVM, to determine the boundary to separate these two groups. Finally, they extract the support vector of SVM as a direction in latent space to manipulate the desired attribute. We then train a stylecode to yaw angle module to predict the step size used to turn the stylecode to its symmetric view. To combine information from both views properly while training our generator, we propose to use weighted mask to combine face information in the overlapping region between two views. As we can see that training generator without using weighted mask, the single view results produce some artifacts on the side of the face. On the other hand, the generator trained using weighted mask didn't produce such artifact. Due to the limited length of video, we encourage audiences to refer to the supplementary material for the procedure of training the stylecode to yaw angle module and that of synthesizing of the weighted mask. Here, we compare our method with other controllable and 3D-aware face synthesis methods based on StyleGAN2, including lifted GAN, interface GAN, StyleFlow, and EG3D. We encourage audiences to evaluate each generated face individually based on the quality and preservation of identity under large angle changes. Interface GAN uses the support vector machine, SVM, to train a binary classifier and takes the normal vector of the decision boundary in the latent space as a meaningful direction. Considering the entire process was conducted in 2D space, interface GAN suffers from the loss of image content as the yaw angle increases, making its results less consistent. Lifted GAN utilizes the depth map as the shape representation and trains a couple of modules to render stably in various perspectives. Compared to interface GAN, lifted GAN maintains a more consistent image content with varying yaw angles. However, it suffers from severe image distortion as the yaw angle increases. StyleFlow achieves disentangled control over different style attributes, including gender, glasses, pose, lighting, and expression. Nevertheless, its results exhibit significant distortion at large yaw angles due to a limitation imposed by the latent space of StyleGAN. The recently proposed EG3D can better preserve shape consistency than interface GAN, lifted GAN, and StyleFlow. However, it also exhibits distortions when the yaw angle becomes large, especially around the eyes. As shown below, our method achieves superior results in terms of view consistency while preserving the quality of the face. One of the advantage of using StyleGAN2 generator structure is that the latent space is smooth, so we can freely interpolate stylecode to form a face which appearance is the combination of two faces. Here we provide an example that demonstrate the smooth transition between stylecodes. Here, we pick two examples to demonstrate that we can control the face attribute explicitly. Using 3DMM as our blend shape, we can adjust the facial expression and lighting by directly manipulating 3DMM coefficients. From the bottom case, the additional displacement map can produce lighting features, e.g., wrinkles, because it changes geometry during rendering.